Howdy, this is Browdy, coming at you with discussion 8.1. This is technically the second discussion of Unit 8, but today we are talking about the mole, so let's just jump right in. Now, we're not talking about the mole on your back or wherever it is, or the mole that is like infiltrated the CIA or like the mafia or something. We're also not talking about the mole that your mom's been complaining about in the yard forever. We are talking about the number, the quantity, the mole. So the first question that we have is, what is a mole and why do chemists use it? So let's think for a second about a dozen. So you've heard of a dozen before. It's a word that represents a number. A dozen represents, well, if you have a dozen eggs, that's 12 eggs. If you had a dozen atoms, that would be 12 atoms. Now, a pair also would be 2. Right? So a pair or a couple means 2. A dozen means 12. Well, a mole of eggs is 6.02 times 10 to the 23rd eggs. Or a mole of atoms is 6.02 times 10 to the 23rd atoms. Now, what does that mean? Why is that such a big number? That's 602 hexillion. So there's 1,000. Right? So one with 3 zeros. And we're going to add 3 zeros every time. So there's 1,000, a million, a billion, a trillion. A trillion is 10 to the 12th. Then there's a quadrillion, I believe is next. Then a pentillion. Then hexillion. And so this number is 6.02 times 10 to the 23rd, or 602 hexillion with 21 zeros after it. But what the heck is that number? Why does it matter? And why have you never heard of it before? Let's talk about that. So a mole, that number that we just talked about, isn't useful to count most things. And so the reason you haven't heard of it before is you've never had any reason to talk about it before. So for example, if we had a mole of eggs, so 602 hexillion, or 6.02 times 10 to the 23rd, eggs. That would be enough eggs to fill the ocean roughly 2 trillion times. So think about that. All the water that's on the earth, all of that, all the volume, how deep it goes, all of the water on all the oceans of the earth. Replace that with eggs. Now, think about how many eggs it would take just to fill a swimming pool or a lake. Well, the whole ocean, all of the oceans of Earth, not just once, not even just twice or a million times, 2 trillion times. If you had a mold of marshmallows, if you laid it out over the entire surface area of the United States, think about how many it would take to just make one layer of marshmallows. But we're not looking at just one marshmallow. We're looking at, or one layer of marshmallows. We're looking at a layer of marshmallows 600 miles tall or deep. If you had a mole of paper clips and linked them together, that'd be enough to wrap around the equator of the Earth. Not just once. 450 trillion times. Now, this is all like approximate math. So if there are 60 trillion cells in a person, again, approximating here, if you took all, and you'll see here that it says 6 billion people, and I've made that 7.55, just because I like to see that we've had 1.5 billion more people since this worksheet was initially made, or since these notes were made. But if you took all 7.5 billion people on Earth and added up all 60 trillion cells per person, that would be in the ballpark of 4.53 times 10 to the 23rd cells, which is only about 73% of a mole, not even 3/4. If you had a mole of dollars, this is my favorite one of all these. If you had a mole of dollars, you could spend $1 billion a second. Remember, a billion is 1,000 millions. So you could spend $1,000 million every second. If you had a mole of dollars, you could spend $1 billion every second, and it would last you 19,086,873 years. It's a lot. It's a lot of money. I'll take some of that. Now, all of that in mind, you haven't heard of a mole before because you've never had any reason to talk about it. All those contexts that we just mentioned are ridiculous. What if we had a mole of water molecules? 602 hexillion water molecules. Well, that would take up a volume of 18 milliliters. My water bottle here holds 1,000 milliliters, or 1 liter. Just 18 milliliters is 1 mole of water molecules. So these examples, not at all useful to measure things in a mole. Water molecules, useful. Okay, and so we're going to talk about something called molar mass. And molar mass is just simply the mass in grams of 1 mole of a substance. So a mole of water molecules, for example. So the mass of 1 mole of a substance is its molar mass. And that's equal to its molecular mass. Now what I mean by that, here's an example. So a mole, or 1 molecule of H2O, weighs 18.02 AMUs, so atomic mass units. That's the weight of 2 hydrogen. So if you remember, if you go back to the periodic table and you look at the any element, so we'll look at hydrogen to start. If you look at hydrogen, it weighs 1.01, and I'm rounding here, AMUs. 1 hydrogen atom weighs that much. That's the atomic mass, right? We talked about that back in Unit 3 when we looked at average atomic mass and why they're not whole numbers and isotopes and things like that. So if you added 2 hydrogen atoms, each at 1.01, and oxygen here as 16.0 or 15.999, 1 molecule of water weighs 18.02 AMUs. We'll explain more of that in a second. But so if that's how much 1 molecule weighs, 1 mole of water weighs 18.02 grams, or its molar mass is 18.02 grams per 1 mole. And so we say that the molar mass is the grams per mole of a compound. And so the unit is grams per mole. So in the same way that miles per hour means miles per 1 hour. If I'm driving 60 miles an hour, that means I'm driving 60 miles in 1 hour. If something weighs 18.02 grams per mole, that means 1 mole of that substance weighs 18.02 grams. And so as we're dealing with atomic mass from the periodic table, I want you to round that to 2 decimal places, and we'll talk about that in a second. But now, why the number 6.02 times 10 to the 23rd? Well, we call that Avogadro's number, named after the Italian scientist who basically coined it or came up with it or discovered it. And that number is the number that relates the mass of, in AMUs, of 1 molecule or 1 atom of something. And if you have 1 mole of that, or 6.02 times 10 to the 23rd of those molecules or atoms, you'll get that same number in grams. That's why that number matters. Now let's look at molar mass. So to calculate molar mass for different elements or compounds, if we have a single oxygen atom, if we want to find molar mass of oxygen, so meaning the mass of 1 mole of individual oxygen atoms. If oxygen weighs 16.0 AMUs, because it's 15.999, which to round up to 2 decimals makes it 16.0, 16.0 AMUs, so it's 16 grams per mole. If we have oxygen gas, O2, an O2 molecule would weigh 2 times 16.0, so an oxygen gas molecule would weigh 32 AMUs, and so it's 32 grams per mole. Magnesium nitrate here. The way we would calculate this is we'd find magnesium on the table and round it, so 24.31, plus how many nitrogens do we have? We have nitrate twice, so 2 N's, so 2 times 14.01, which is nitrogen, plus 3 oxygens times 2, so 6 oxygens, which are 16.0, And so when that all adds up, magnesium nitrate has a molar mass of 148.31 grams per mole. Okay, so that's molar mass. Now let's see how and why we're learning this. So if you think back to 8.0, we learned the factor label method and all about converting units. And the reason that the mole really matters is because it allows us to convert between things. And we'll see this more as we start applying this to chemical equations. But you can kind of think of moles as our base unit. The same way that if I were to go from kilograms to milligrams, okay, kilograms, there's 1,000 grams in a kilogram. And there's 1,000 milligrams in a gram. So if I wanted to convert between the two, I always suggest that you go from one to the other. Or rather than going from one directly to the other, you stop at the base unit. So I would convert from kilograms to grams, and then from grams to milligrams. And the same thing works here. So to convert between atoms and mass, so if I know how many atoms I have of something and I want to know how much that weighs, or vice versa, I have to convert to moles first. And so let's look here first, because we talked about molar mass most recently. If I have the mass of something and I want to convert to moles, what I use is the molar mass, specifically from the periodic table. That's how I find that, right? Now, if I have the number of particles that I have of something, so if I know I have, 4 times 10 to the 24th particles of a substance. So particles is kind of like the general term that can mean atoms if it's an individual element, or molecules if it's a compound. I could use Avogadro's number, 6.02 times 10 to the 23rd, to convert to moles. And I'll show you how that works. So these are actually conversion factors. And I'll explain. So I've got 3 example problems here. The first one says, how many moles of water are there in a water bottle filled with 500 grams of water? So that's half of this water bottle. How many moles of water are there in a water bottle half that size? So we start just like we did doing any factor label method stuff. We start with what we know, what we have. 500 grams of water. And I put it over 1. Now, to convert that to moles, we'll have moles on the top and grams on the bottom. But what do we use? What conversion factor? Well, we use the molar mass, because if this is how many grams we have, and I know how many grams are in a mole, that's what molar mass is, grams per mole, well then I can just convert, right? And so in 1 mole of H2O, I will have 18.02 grams of H2O, because this is the molar mass, right? 2 hydrogens plus 1 oxygen. Oxygen is 16, hydrogen is 1.01, so there's 2 of them, so 18.02. I divide, I can cancel grams, and I end up in moles, and I get 27.75 moles of water. And now you always have to ask yourself, does your unit and your number, your answer, make sense? Well, if this is how many grams are in 1 mole, and I have this many grams, well, yeah, having that many moles is a sensible answer. Let's go to number 2. How many molecules of carbon dioxide are there in 6.23 moles of CO2? So we start with what we know, 6.23 moles of CO2, and I've got that right here. Put it over 1, put it in parentheses, multiply it by the conversion factor to get to molecules, which is essentially the same thing as particles, right? Well, what's the conversion factor? Well, I know that 1 mole of carbon dioxide is the same thing as 6.02 times 10 to the 23rd molecules of CO2, because that's what a mole means. It means that many molecules. It's just a conversion factor, right? The same way that 2 apples were worth 3 bananas. Well, this is the same thing. We're just using it in chemistry terms. And since we started in moles of CO2, we put 1 mole of CO2 on the bottom, and we put molecules of CO2 on top. And so we multiply it. Our answer that we get is 3.75 times 10 to the 24th molecules of CO2. Now, if you have questions about how to do this math or how to put these things in your calculator, just ask me individually rather than me trying to explain it. On here, it kind of just depends on a case-by-case basis what calculator you're using and things like that. But I'd be happy to help. But now think, does your answer make sense? Well, okay, if I've got 6.23 moles, and I know that there's this many molecules in 1 mole, well, what's this number times 6.23? Yeah, that's a logical answer. So it checks out, it makes sense. And let's talk about the last one. So here, we want to know how many aluminum atoms are in 5.23 grams of aluminum foil. So I'm starting with the mass, 5.23 grams of aluminum over 1. Aluminum foil is just pure aluminum, just hammered really thin or flattened. And so I have 5.23 grams of aluminum to start. And I want to know how many aluminum atoms there are. I have no way to convert directly from grams to atoms, but I can go through moles. And so I start with 5.23 grams of aluminum, and I want to convert to moles. And I do that using molar mass. And so I calculate, or I find on the table, I find aluminum, find its molar mass, which is 26.98. And so if its molar mass is 26.98 grams per mole, that means there's 26.98 grams of aluminum in 1 mole of aluminum. And so I arrange them like this with moles on top, grams on bottom. I can cancel grams of aluminum, and now I'm in moles. And just like in 8-0 or using the factor label method, we can just stack on conversion factors. We don't need to calculate it out every time. And so now I'm in moles, and I can convert directly to atoms or particles. And we know that there's 6.02 times 10 to the 23rd atoms of aluminum in a mole of aluminum. So we put moles on bottom because that's what we're getting out of. We're going to atoms, so that's on top. I can cancel moles, and now all I need to do is just do the math. And conveniently, there's just ones everywhere. So really, I have 5.23 divided by 26.98 times 6.02 times 10 to the 23rd. And I end up with 1.17 times 10 to the 23rd atoms of aluminum. And we say, okay, does that answer make sense? Well, how many atoms are in this many grams of aluminum foil? Okay, so we have 5.23 grams. And okay, how is that related to a mole? Well, if the molar mass is 26.98, well, that's significantly less, right? That's less than half for sure. And so it might even be less than a quarter, but it's right around a quarter, okay? And so if we have this to start, and we know this many are in a mole, and we know this many atoms are in a mole, well, our answer should be less than this, but close. And it is. That's what we've got. So our answer makes sense. So all the same rules as the normal factor label method apply. We're doing the same system. This is why I kind of taught you this format of writing out equations and things like that and conversions. All the same things apply as before. Writing our units, canceling out our units, using parentheses, having fractions, all that, circling our answers. But just now, make sure that when you're done with everything, because we're using different units, just make sure your units make sense. Okay? That's all I've got for you. That is discussion 8.1. That is the mole. That is Avogadro's number. So I hope this has been helpful. I hope this has made sense. And of course, as always, if you have any questions, you know how to get a hold of me. Canvas, email, and just talk to me after class. Again, hope you're doing well. I hope this has been helpful. And I'll see you in the next one. Take care.